With more GPU power, it's generally acceptable to then start adding layers. But of course, as always with training, we need to be careful that adding more layers to my CNN might result to overfitting, right? So as always, just we need to be careful about performing proper cross-validation protocols and, you know, not shooting ourselves in the face with just naively adding more layers. So all of these ingredients need to really come together. The training optimization, the data sets, and the GPU power. So let's look at some of the architectures that you know, have been important throughout. So the Linnet architecture is one of the earliest convolutional neural nets that significantly impacted the field of deep learning for image recognition, developed by Yann LeCun and his colleagues in the 1990s. They went, or maybe 1980s and then 1990s, they went through 5 different iterations of it back then, from Linnet 1 to Linnet 5. Originally designed for the task of recognizing handwritten digits, and then for, as we said, automatic sorting of envelopes by the USPS. So right, they went through 5 different iterations, as I mentioned, and all of the versions included some combination of convolutional layers and pooling layers and nonlinearities, and then followed at the end by the fully connected. So we had convolutions, we had pooling or subsampling, you repeated that multiple times, and then you have the fully connected layers in the end. Now, if we were to, for a second, just look at this is a very big table, but I want to draw your attention to somewhere in this table, I've just put all the layers together, so convolution 1, pooling 1, and then etc., and then fully connected 1 and fully connected 2 at the end. And I want to draw your attention to a specific part of this table that characterizes Linnet 5, is it? That's a bit alarming. And that is this column right here. So the number of learnable parameters, or the number of weights. Is there something alarming with this column of data?
Could you rephrase again the question?
Right, so here I'm showing a table of all the characteristics of Linnet 5. In every row, we have one of the layers. And you can see that, you know, some of the layers, of course, don't have learnable parameters, like pooling doesn't have any parameters. But the convolution layers and the fully connected layers, which are highlighted at the bottom of the table, all have learnable parameters. And it seems like the fully connected layers have a lot more learnable parameters than everything else in the network. Right? So if overall there's on the order of maybe 70, 80,000 learnable parameters, a majority of it is in the very final part. Right? And so it's basically dominating everything. The fully connected layers take up an overwhelming majority of trainable parameters. And we said that the power, at least our intuition is telling us that the power of CNNs comes not from the fully connected part, but from everything that comes before it with the hierarchical abstract representations and the close to linear separability that it enables through the convolution layers. So it's a bit disappointing to see so many of the learnable parameters be somewhere else in the network. And so as you can imagine, newer and newer architectures try to overcome this imbalance between learnable parameters of the convolutional layers versus the fully connected layers. And so in 2012, we saw AlexNet. AlexNet was the network that, you know, caused that big drop in error rate, or a big increase in performance. So debuted in 2012. It had 8 weight layers now. Linnet had like 2 or 3, but now this has 8 weight layers. So you can imagine the balance is now tipping in. The balance of learnable parameters is now tipping in favor of the convolution part. On the ImageNet challenge, not on MNIST, which was close to 99% already, but on the ImageNet challenge, it was such a difficult task that they no longer looked at top 1 error rates, but they looked at top 5 error rates. So they would say, among all the 1,000 classes that we could predict, let's just take the top 5 values and assume that one of those is one of the top 5 predictions, the correct prediction. If so, we're going to say that we did it correctly. And 16.4% top 5 error rate, and then it kicked off everything else about the deep learning boom over the past decade. Now, an interesting historical fact is, why did this model have 2 identical looking parallel branches? Does anyone know? So it's a tidbit from yes, Mustafa?
One convert 2D matrix into 1D flatten, and then we want to reduce some neurons. That's why we introduce less number of neuron in next layer.
Okay. But the question is, why is it that these two branches and they're identical? Why have two? Why not put it all together in one branch? So the reason for it's not anything to do with, the computation, at least on paper, but it's because the hardware at the time didn't enable this whole model to be loaded into it. And that's what I said
Yes,
about engineering
I know.
challenges.
They
Engineering
use
challenges
two
at the
GPU.
time. Yes, Mustafa?
I said they use two GPUs to train for ImageNet.
Right, exactly. So the reason we have two different branches is that so that they can run it on two, back then, GTX 580, 3 GB GPUs in parallel. And it took 5 to 6 days to train. There was a lot of engineering that went into making something like this work. I mean, the ideas, the basis of the ideas were the same as before. We have convolution layers, we have element-wise nonlinearity, we have pooling, and then we have a fully connected layer to do the classification part. But making it actually work was very difficult. And that's why a lot of these, state-of-the-art models that are coming from companies today, the basis of them is probably all that we see, from the 2017 Transformer paper, with a bit of tips and tricks here and there and some optimization steps added in and some magic dust, but it's really not that different. But actually realizing it at scale is a major, major engineering challenge to see. And back then, one of the clever ideas that was implemented was we can't fit everything on one GPU, but we want to have the power, so let's figure out how to connect them on multiple GPUs. Something that is probably a one line in the code right now. Okay, so in this architecture, as before, with Lynette, we had two different parts. We had the fully connected part for classification. We had the convolution part for feature extraction. And now maybe there's a bit more balance between the learnable parameters between each. The next model said, you know what, we're just going to get rid of the fully connected part altogether. We're going to go a fully convolutional approach. And so enter GoogleNet or GoogleNet, which scales up even further. Now it has 22 weight layers. And the motivation was we're going to reduce this, although it has more depth, but we're going to reduce the number of parameters so much that we could run it on a cell phone. And they aggressively reduced the parameters by removing the fully connected layers altogether and becoming fully convolutional. And remember the one-by-one convolutions that we talked about? So each of these parts here is one of those inception modules that we said is going to be doing a bottlenecking, taking different paths and reducing the number of parameters for us. And now we got from, 16% to 6% error rate on ImageNet. But of course, if you think we stopped there, of course, we did not stop there. So the next year in 2015, we have the residual network architectures. And these now have like 50 layers, 100 layers, 300 layers. And so when you stack layers like this, you run into other forms of problems, like how do we optimize and how do we make sure that the gradient is passed back correctly? And so some other clever inventions were created, like skip connections. Skip connections, you can see them here, like they're connecting multiple layers together so that gradients could still pass through. And so these models start performing so well that we went back to looking at top 1 accuracy rather than top 5 accuracy. And the funny byproduct of this is that these models also started to detect errors in the data set itself. So not only were they not making mistakes, but upon inspection of the very few mistakes that they made, they realized that, oh, this particular instance was mislabeled altogether. So that's how good these models got.